All right, friends and neighbors, welcome back. This is Chapter 11 of the CCNA, Perspectives on IPv4 Subnetting. So these are a lot of big ideas, not a whole lot of demos today, but lots and lots of ideas. And I think it's really important to hear these ideas a couple of times. So a lot of this stuff in this video will also have entire chapters dedicated to. So we are starting part 4 in the sort of layer 3 IP addressing, IP subnetting sort of section. Lots and lots of big ideas, as I mentioned. The exam topics that we're covering will be configuring and verifying IPv4 addressing and subnetting, and then describing private IPv4 addressing. So we'll do a little bit of both of those today. I moved the do you know this already stuff to the end so that we can sort of use this video as support for the answers to the questions. And then we'll do our look ahead, just a little bit about IPv4 class full networks. So when we start talking about subnets, I always find it really, really difficult to understand subnetting if you don't understand a little bit about where we came from. Now, again, this will be one of those that we have a whole video dedicated to this one, but it all starts with what we call our classes of addresses, A, B, C, D, E. And E is sort of reserved, so we don't use that very much. And D is multicasting, so we only assign classes A, B, and C to networks with hosts. So you'll never have a network that begins with a class D address space. Now, when we're talking about addresses in a network, one of the ways to identify that they are in fact in the same network is that they share the beginning values, or what we call the beginning octets. So the class B network example that we have here is 172.16.0.0, and then all of the hosts inside that address space will share 172.16. So we just count up through them all. In this case, there are 65,536 possible addresses. So you just start counting. And so 172.16.0.0 is the beginning, and then 172.16.0.1, 02, 03, until you get through 256, and you wind up with 172.16.1.0, and you do it all over again, and then 2.0 and 3.0, until finally you get all the way to the end of the address space, which is 172.16.255.255. So counting through a network works that way with every one of them, but we'll find out that different networks have markedly different sizes. Now, it is sort of overkill to have a network of a couple of hosts and then have some enormous address space like the one we just described. So when that happens, we often subdivide a network into subnets. So we do it for a lot of reasons, but one of them is that when you have a growing network, having too many nodes on a particular network starts to jam up the network with too much traffic. And so we split the nodes up into groups. How and why we build the groups, well, that's part of your design discussion. So as an example, inside the 172.16.0.0 address space, we might have a subnet that is 172.16.4.0. So it lives inside 172.16, but it's cordoned off as sort of a separate thing. And then if we had a sample topology, we might have a whole bunch of these subnets inside this large address space. And this is the diagram from the book chapter, right? In this case, all of these networks, right? If you look here, there are 5 networks. All of those networks reside within the 172.16.0.0 address space, but each one of them could be their own subnet. Now, in this case, all of these subnets are numbered in the exact same way. So we have the 1 net, the 2 net, the 3 net, the 4 net, the 5 net, but it doesn't have to be that way. They can be different sizes, so we can apply different rules for the subnets. But let's not get ahead of ourselves. When you're trying to decide what your subnetting scheme is going to be, right? How are you going to divide up this large address space, this large network? What we do is we say, well, what do we need operationally? And by that we mean, okay, how many departments do you have? How many different buildings? Where are people located? What are your security concerns? And these sort of feed into how many networks do you need, or how many subnets do you need? So why pick a particular subnetting scheme? Well, We might want to say, I've got a whole bunch of people here that belong together, and I have another group of people that's much smaller, they belong together, and so we have different sizes. It might be that you just say, look, I just want to do the same thing for everybody. So when you get down to the business concerns or how you're going to put things together, we start asking these kinds of questions. Along with that, right, how do you want to split up the host? Do you do it by physical location? Do you do it by department? Do you do it by security needs or particular groups? So as an example, at RIT, we might split things up based on staff and faculty and students, or by building. Do you think that your company or your organization is going to grow? And so if you use up all of your address space but have no room for growth, well, then you're going to have to renumber everything later on. So a lot of times we want to leave room for growth. And again, this question of are all the subnets the same size, right? So in the diagram above me here, we can see that it's a very similar numbering scheme. It turns out that all these subnets are the exact same size. They all are 256 possible addresses in each one, 254 usable. Now that might work just fine, but we might decide, well, on a point-to-point link, like between routers, that's terribly inefficient. We might find out that some of our networks have much larger number of hosts. And so it might be the right thing, but it might not. So when you subnet a network, what we're looking to figure out is what are our actual needs, right? How many subnets do we need? How big should they be? Then we got to design it. We got to figure out the numbering scheme. We got to figure out what our masks are going to be. And then we got to figure out what the numbers or what the addresses of all the networks are going to be. And then we got to put it all together. Then we got to build the thing. We have to implement it, figure out where the subnets are going to be assigned, and then make our addressing for the hosts and the interfaces. Now, a really good question at this point is, what is a network? Well, if we start with the classes, we'll do class A, B, and C here. These three classes are all about creating networks that are really, really big, medium-sized, and then much smaller. So all addresses of a particular class fall in a particular numerical range. And if you break it down into binary, they share a binary pattern as well. But class A's are all 0 to 127. Class B's are 128 to 191. Class C's are 192 to 223. And then I've given you some examples. In a little bit of foreshadowing here, what we also want to remember that each one of these classes have a default or natural mask associated with them. So class A's are 255.0.0.0 and so on. The mask is really, really important to us. It tells us how big our network is, and it also tells us the address of the network. Now, all of the hosts in a particular network share the same prefix. That is to say, they share the same beginning. So if two nodes both begin with 10 and then there's 001 maybe, or 10.999, 9.9.9, if they share that mask of 255.0.0.0, they're all on the same network. So they share the same prefix, the same mask, and usually the same router or gateway. All hosts in a particular network will be in the same VLAN. Now, when we take a network and we break it up into subnets, what we're really doing is chopping up that network into smaller spaces. Each one of those spaces needs a gateway, needs a mask, and each one of them behaves exactly like a network. It's just a chunk of address space. Now, when you're trying to figure this out, you might be given a diagram or a description of what is needed, right? You might say, well, here's our network diagram that we have. We've got growth, we've got changes. What should we do for subnetting? It might be that you simply say, all right, we're coming up with an initial design. We have 5 departments with 50, 30, 20, 20, and 10 users respectively, right? It might be that. So then you say, all right, well, what's a good way to lay out the subnets? What's the address space that I'm going to divvy up? And what might be a good way to lay things out? Now, you might do something that's highly customized, right? You might build a network that's just the right size for 50 users, another one that's just the right size for 30, another one that's just right for 20, and so on. Or you might just say, you know what? let's just make every subnetwork the exact same size. So these are valid approaches. You just need to think about what you're going to do when you're dividing up the address space. Now, this is part of a diagram from the chapter, and it just shows that you really never know by looking at a diagram what number of networks you actually see. What is the logical topology? You see the physical topology, but it's really hard to know what's going on there. In this particular case, right, you see 4 switches interconnected, and then they're connected to a router. Without the label there that says we need 12 VLANs, you would never know that. And if you need 12 VLANs, well, you need 12 subnets. So that feeds into your subnetting scheme. Now, if you understand network masks, you are ahead of the game, right? That is awesome sauce. You really want to be able to dive into and understand the manipulation of network masks. So when we're breaking a network up into smaller subnetworks, or if we are gluing networks together into much larger address spaces, super networks, the masks are the way that we manipulate all of this. Masks tell us about our current network. Masks are used in routing tables. Masks tell us the size of a particular network, so the range of hosts that might be on that network. So masks are really, really important. So as an example, we have a Class C network, 200.199.198.0, and it has a mask of 255.255.255.0. Now, this is a Class C network, so that's the default mask. Now, the way to think about masks is that you have to realize that when you're looking at all those 255s, it's actually binary. So the binary version of the mask is, 1.1.1, and so on, until you get to the all zeros. Another way to write this mask would be /24. We count up the number of ones and we write /24. That's called CIDR notation, and you'll see that quite a bit. But an important thing to realize about the mask is that the ones tell us the network portion, and the zeros show us where the hosts are. So in this particular case, we see that there are 24 bits allocated to the network addressing and 8 bits allocated to the host addressing. So with 8 bits, there are 256 possible addresses. So the range of those addresses would be 200.199.198.0 to 200.199.198.255. That's 256 possibilities in that address space. But wait, there's more. What if we decided that that was too big? What if we wanted to chop this up into subnets? So what I just told you about the mask is, if you look above me here, right? We divide up the network address or an IP address into the network specific portion and the host specific portion. And that's it. That's what the default mask does for us. But if we decide to subnet this, then we have to realize that there's a network field, a host field, but right in the middle is also a subnet field. These are the bits that we're going to manipulate. Now there's a very nice pattern that we can get used to seeing, and we'll talk more about that in another video or in some of the supporting material for this video. But what we want to realize is that we're manipulating the ones and zeros in the mask and therefore creating a subnet field. Okay, so this address space right now has 256 possible addresses. But the lowest address, .0, that is the address of the subnet or the network. The highest address is called the directed broadcast, the 255. Now, neither one of these addresses can be allocated to hosts, or they shouldn't be. So what that really means is that the usable addresses in a network or subnet is actually 2 less than the total number of addresses in the space. So the way that you figure this out is you say, how many bits are in the hosts? Well, there were 8 bits. So 2 to the 8 minus 2. That brings us 256 minus 2, or 254 usable. And that's true no matter how big your network is, and no matter how many subnets you've created. Now, the minute we start messing around with the mask, we're moving from what we call class-full networking to classless networking. And that's what this image above me is all about. So how does this work? Well, when we break up a network, we're going to add that subnet field. So in the earlier example of 172.16.0.0, when we break that up, we're stealing bits from the host portion. So 172.16.4.0 is actually in the host portion of the network. So the bits that we manipulate are going to be in the third octet in this particular case. In the example that we're doing, 200.199.198, the host portion is in the last octet, or begins in the last octet, right? So the bits that we would start manipulating are all the way in that last octet. And so there's an example there. Now, subnets can be any size that you want, as long as they're based on a power of 2. The number of subnets is also based on a power of 2. So we create 2 subnets, or 4 subnets, or 8 subnets, 16, and so on. And a subnet will have 2 hosts in it, or 4 hosts, and so on. 256, 512 hosts, 1,024 hosts. So this is how we have to think about this. It's in terms of power of 2, because every time we manipulate the bits, we change one of the bits to a 0 or one of the bits to a 1. We're either cutting the address space in half or doubling it, powers of 2. So when we make design choices, what we're going to do first is start with some kind of address space. Typically, this will be a class A, B, or C. Now, how do you get address space? Well, let's assume for just a second that you could get a class A, B, or C. Originally, you might have gotten it from IANA. IANA is the Internet Assigned Number Authority. They're in charge of this whole thing. So you can see all of the numbers associated with networking out there at IANA. Well, most of them. So the way that address space is allocated is that it goes from IANA down to the regional internet registries and then to ISPs. The graphic above me is the regional internet registries. So I'm in North America, so that would be Aaron. I would say, well, IANA, I need a class of address, and then my RIRs would have control of a certain chunk of the internet address space, and that would be doled out that way. Well, today the problem is that that's not how we allocate IP addresses anymore. One reason is because we're actually officially out of address space, but another reason is that the class full addresses are pretty much gone, and it's a terribly inefficient way to manage IP address space. What you actually end up doing is you get a chunk of public address space from your ISP. How many addresses do you need on the public internet? Here is your address space. But you can also go with private addressing. This is the addressing that's associated with RFC 1918 addresses and network address translation. Today, what we do is we manipulate the masks to make them more efficient, but we also have to deal with the idea that there are no new addresses to give out anymore. So the ISPs control a lot of address space. So IANA gives it to the RIRs give it to ISPs, and the ISPs dole it out to customers. So let's remind ourselves quickly about classes. We started off with this class-full address space. We now know that this is not only inefficient, but there aren't any left. But we can see that class A's have a range of 0 to 127. That means there aren't very many class A networks out there. But each one of the class A's has an enormous address space for hosts, 24 bits of addressing for hosts. So each class A network has 16 million possible addresses. In a class B, well, there are more of them. There are 2 bytes allocated to class B's, and they range from 128 to 191 in the first octet. But there are also 16 bits allocated to hosts. So each class B is smaller than a class A, but still has 65,000 possible addresses. And class C's come in all the way at the bottom. They're the opposite of class A. There are lots and lots of Class C addresses, but each one of them is only 256 possible addresses and 254 usable. So that's kind of how we started, right? Inefficient. And the thing that we want to remember is that the mask tells us the network portion and the host portion. So the two problems that we have, at least in terms of IP address space, is that one, we ran out. What do we do about that? And two, there are lots and lots of people at this party called the internet. That means routers have really, really large routing tables. And so it becomes difficult to search through all of those entries. So we do lots of stuff to mitigate these particular problems. One is that we use CIDR notation, right? So we can manipulate that mask all over the place to be more efficient with it, but also we can create supernets to reduce the size of routing tables through a process called aggregation. So in subnets, we break the address space up into smaller chunks, which means that each network or subnetwork is going to be smaller. So we make the host portion smaller. We steal bits into the host portion. In supernets and aggregation, we glue networks together. So we want to make networks bigger. So we provide more address space for hosts. And so we steal bits into the network portion. We convert ones to zeros. So that Class A example just says, if I was going to start manipulating the mask, that's the area that I would start right there. Now, it might surprise you to know that we've known about the address space depletion issue for a long time. So there have been plans in the work to replace IPv4 all along. And we officially ran out of address space almost 10 years ago. So there have been a couple of solutions. In addition to CIDR making things more efficient, there was this whole idea of private addresses and network address translation. So in the graphic right above my head, we can see that there are two networks that use the same address space, 192.168.1.0. How do networks get away with using the same address space? Well, through the miracle of network address translation, everybody can use the exact same address space, and we just get translated to a single public IP address out on the public internet, that is on the outside of the router. Now that was supposed to be a short-term solution. The long-term solution was IPv6, but IPv6 had trouble getting traction. One of the reasons is because network address translation works so well. We all do it. It's fantastic. And so because of that, IPv6 hasn't really caught on as much as the designers may have hoped. Now, along with network address translation, we have three classes of private address. There's a class A, B, and C. And so the tennet is allocated towards private addresses. In fact, most companies, when they go to private addressing, they use the tennet. There's a class B address range, 172.16 to 172.31. There are 16 large class Bs. And then there are a bunch of class Cs, and those are the ones that we use at home quite a bit. You'll see those on wireless home gateways. Now this also means that the range of addresses for the classes have these carved out of the space. So where we said a class A range would be from 0 to 127, we would now have to say, oh, it's 0 to 127 except for the tennet, because we can't use these addresses on the public internet. So here is the design example from the book, the 172.16.0.0 network with the 255.255.0.0 mask. We want to create 200 subnets, and each subnet has to have 200 hosts. So this will be a one-size-fits-all sort of thing. The first question is, how many bits do we need for 200 subnets? Well, if we stole 1 bit from the host portion, we would be creating 2 subnets. Well, that's not enough. 2 bits gives me 4 subnets. 3 bits gives me 8. It turns out we would need to steal 8 bits to give us 200 possible subnets. And this is because the subnets have to be based on a power of 2. If we did 7 bits, that would be 128. It wouldn't be enough. So the red section of the mask would be converted to ones with our new mask of 255.255.255.0. All right, how about the hosts? How much space do we need for hosts? Well, it turns out for this one, we also need to steal 8 bits because we need 254 usable addresses per subnet. We can't do that with 7 bits. We would need 8 to do it. Now, when you're looking at a problem like this and you're creating your subnets and you're creating your hosts, the math has to work out. So in this case, we created 256 subnets and there were 256 hosts in there. So that worked out. If you said I need 500 subnets and each one of those would need 200 hosts, well, that wouldn't work, right? The math would not work for the bits that we have available. So to continue on with this example, we would start counting through the subnets that are there, and we would see that the first one is 172.16.0.0. We always start at the class full, and the range would be 172.16.0.1 to 172.16.0.254 with the .0 and the .255 the special addresses that we don't give to hosts. The second subnet would be 172.16.1.0, and the range there would be 1.1 to 1.254. All right, when it comes down to the implementation, now it's time to build, right? You figured out what you want to do. Now it's time to assign things to interfaces and put your hosts on the map somewhere. So you have to decide where your subnets are going to live and how they're going to flow together, right? Are you going to do this sort of numerical order? How many hosts are going to eat each one? We also find out that sometimes we don't use all of the subnets, right? We want to have some for growth. So which ones are you going to actually use and which ones are you going to hold back? We also find out that we often don't use all of the addresses in the subnet. So all the way on the side of the diagram, right, over here and over here, we might have lots and lots of hosts. So we might use up a lot of the addresses in the subnet. But right here, between the routers, this is a point-to-point link. So this might not use up very many addresses at all. So that's where we kind of have to go, is the one-size-fits-all the right way to do this? In addition, on a point-to-point link, right here or right here, probably not using DHCP. But here we certainly might, and here we might, because we've got hosts there. So in that case, every subnet needs a DHCP server or a relay agent to get to a DHCP server. All right, so now that we got a lot of these big ideas out of the way, let's do the do you know this already? So host A is a PC connected to switch 1 and assigned to VLAN 1. So it's in a network, and that network belongs to a VLAN. Which of the following are typically assigned an IP address in the same subnet as host A? Choose 2. Well, your router is always going to be on your network or your subnet, and other hosts in switch 1, VLAN 1 would also have to be on the same network. Question number 2, why does the formula for the number of hosts per subnet, 2 to the h minus 2, require the subtraction of 2 hosts? Well, now we know what that is. The reason for that is that we have one address for the network or subnet itself and one address for the subnet or network broadcast. So 2 to the h minus 2. Question number 3, a class B network needs to be subnetted such that it supports 100 subnets and 100 hosts per subnet. Which of the following is workable for the number of network, subnet, and host bits? Choose 2. Well, we know that if this is class B, we have 16 bits that we can fool around with, right? 16 bits in the host portion. And we know that if we had to create 100 subnets and we needed 100 hosts, each one of those would require a minimum of 7. We also know that it's a class B, so there's 16 bits in the prefix that we can't touch. So the first number is going to be 16. We can't touch that. The second number, well, we can get away with anything 7 or above, as long as the two numbers add up to 16. So that would be subnet 8 and host 8, or subnet 9 and host 7. Question number 4, which of the following are private addresses? Choose 2. Well, we just saw the graphic, right? It's 172.31 was the answer, and 192.168. Both of those fall in those ranges. Question number 5, which of the following are public IP addresses? Choose 3. Well, anything outside of the private addresses from RFC 1918. So the answers here are the 9, the 192.1, right? It's not 168. Careful on that one. And then the OneNet. None of these are private. They're all public. Question number 6. Before Class B network 172.16 is subnetted, what parts of the structure of the IP addresses in this network already exist and with a specific size? So this is referring to the structure of the network itself. The answers there were A and C. This is a little bit of a tricky question. So the network and host portions are already there, and we're going to manipulate this by putting a subnet field in there and determining what the addresses are. Question number 7, consider the size of the network, subnet, and host parts of the Class B network 172.16.00 without any subnetting. Compare that to an updated plan that uses one mask for all subnets. Which answer best describes the size changes? Well, remember that we are going to be stealing, the minute we subnet, we're going to be stealing bits from the host portion, and that means the host part has to get smaller. So our Chapter 12 look ahead, we're going to take a deep dive into class-full IPv4 networks. So we're going to tear into those classes and learn a little bit more about those and maybe what Class D is all about. We're going to also take a look at the context for public networks and CIDR blocks, right? The RFC 4632 is a very, very important RFC that talks about the classless interdomain routing. Now, in all of this space, there are several unusual network IDs and different kinds of broadcasts. So we'll take a look at all of that. All right, so this has been Chapter 11, Perspectives on IPv4 Subnetting. Lots and lots of big ideas. So we talked about classful versus classless, a little bit of CIDR, subnets, maybe supernets, and of course masks. Really, really important masks. We know that we're out of IPv4 addresses. We know that NAT and IPv6 were some of the solutions for that. And we talked about planning your scheme, your subnetting scheme, and then the layout, how to actually implement it. So we'll do all of these in much greater detail. Many of them have their own chapters dedicated to them. And the channel, of course, has lots of support stuff, and I'll include all of those links, or a whole bunch of those links, in the show notes. Well, thanks for watching. Thanks for listening. And whether you were on a network that existed before 2015 or you were one of the ones that caused us to run out, may your packets always reach their destinations.